Hello students, welcome to the digital classes. We will continue with electricity, and in the previous class we have seen that electricity is part and parcel of our life. Also, electricity to our lifestyle is like oxygen to our life. Without electricity there is no life. Let us have a quick recap on what we have done in the previous class. We have discussed electric current is defined as amount of electric charge passing through a cross section in 1 second. The formula for electric current is the amount of charge flown by time. So, I is equal to Q by T, where Q is the charge and T is the time. SI unit of current is coulomb per second, which is equal to ampere. We have seen that just like objects roll down if there is difference in heights, electric charges move if there is potential difference. A battery maintains constant potential difference across the wire. The work done by the chemical force to move 1 coulomb charge from positive terminal to negative terminal is given by W by Q, which is called the potential difference or EMF of the battery. We discussed Ohm's law. Ohm's law says the current in a conductor is directly proportional to the potential difference applied across the conductor at constant temperature. Current I is equal to V by R, where R is resistance of the conductor. Let us discuss Ohm's law a little more in detail. Ohm's law, which says the current in a conductor is directly proportional to the potential difference applied across the conductor at constant temperature. Here the resistance is constant for the conductor and hence it is constant at temperature. Hence, the Ohm's law is valid only at constant temperature. Electrical resistance of a conductor is the measure of opposition to the flow of electric current through it. In simple words, resistance of a conductor is the property by virtue of which the conductor opposes the flow of electric current through it. The SI unit is ohm and the symbol is omega. We draw resistance with the zigzag lines as shown in the figure. So, any wire which has resistance or which offers considerable amount of resistance is called a resistor, and if the resistance is very less, then we say the wire is a very good conductor, and if the resistance is very high, we call it as insulator or a very bad conductor. Resistors are conductors which offer resistance. If the conductors have very less resistance, we say they are very good conductors. If the conductors have very high resistance, we call them as bad conductors or insulators. All the conductors which obey Ohm's law are said to be ohmic conductors. So, all the wires are ohmic conductors. Also, point to be noted that Ohm's law is valid at constant temperature only. If the temperature changes, then Ohm's law will not be held good. So, there are some devices or wires where the current is not always proportional to the voltage. Such wires or conductors are called non-ohmic conductors. So, non-ohmic conductors are those which do not obey Ohm's law. We have silicon, germanium or other semiconductors, and the devices which are made from semiconductors like diodes, transistors, etc., which are used in many of the electronic gadgets. These conductors, they do not obey Ohm's law. Now, let us solve a numerical on Ohm's law. Find the resistance of a conductor if 0.1 ampere current flows when 10 volt is applied across the conductor. From Ohm's law, we have V is equal to IR or R is equal to V by I. So, the voltage which is 10 volts and the current is 0.1 ampere. So, resistance is equal to 10 volts by 0.1, which is equal to 100 ohm. So, the resistance of the conductor is 100 ohm. Let us do another numerical. Find the potential difference across a resistor of 1000 ohm if 0.06 ampere current flows through it. From Ohm's law, we have V is equal to IR. So, the potential difference is 0.06 times 1000, which gives us 60 volt. The potential difference across the resistor is 60 volt. Children, now from Ohm's law, we find that V is equal to IR and current is equal to V by R. That means, for a constant potential difference which is applied, if the resistance is more, then the current is less. If the resistance is less, then the current will be more. Here we can look at triangle in which we can write V, I and R as shown in the figure. If you want V, close V, you get IR. If you want I, close I, you get I is equal to V by R. If you want R, close R and you get R is equal to V by I. So, this is a triangle and a technique which you can remember this formula. We have seen that current is directly proportional to potential difference, and if the potential difference is constant, the current depends on resistance. So, if you are changing resistance in a conductor, or if you are changing resistance of a particular device, then you can change current in the device. So, to increase the speed of a fan, you can increase current by reducing the resistance. So, when you are turning the knob, you are actually reducing the resistance, thereby increasing the current, and then the speed of rotation will increase. Similarly, to increase brightness, we reduce the resistance so that the current will be more, and thereby the brightness will increase. Let us see how resistance will change, or on what factors resistance depends on. Factors affecting resistance of a conductor. Resistance of a conductor depends on the material the conductor is made of, the length of the conductor and the area of cross section of the conductor. Resistance is directly proportional to the length of the conductor. When resistance is directly proportional to length, greater is the length, greater will be the resistance. So, we can see two conductors here of equal area of cross section, but different lengths. If the length is less, then the resistance is less. If the length is more, then the resistance is more. So, greater is the length, greater is the resistance. Lesser is the length, lesser is the resistance of the conductor. Resistance of a conductor is inversely proportional to the area of cross section. R is inversely proportional to area. So, we write it as R proportional to reciprocal of the area. Now, consider two conductors whose lengths are same and the areas of cross section are different. Lesser is the area, greater will be the resistance. Greater is the area, lesser will be the resistance. So, greater is the area, lesser is the resistance, and lesser is the area, greater is the resistance. Children, you may have noticed that wires of some devices are very thin. Can you give some examples? Yes, you find wires of earphones to be very thin, because if they are very thin, the current which flows through that will be very less, and that small current is enough for the earphones to function. Whereas, there are some devices which have to draw more current. Example, refrigerator, washing machine, AC. If you look at the plugs of those devices, they are very thick. So, the area of cross section is more, so that they draw more current, so that their current is more and they can function easily. If the wires are thin, if you are using a thin wire for such devices, easily they may get heated. The heating effect of current will be discussed in the next class, but we can understand that lesser is the area, then greater will be the resistance. If resistance is more, then the current will be less. Children, now combining these two, we get resistance directly proportional to length and resistance is inversely proportional to area. Combining these two, we get resistance directly proportional to length by area. So, if you remove the proportionality sign, we get resistance equal to a constant rho, which is constant of proportion. So, resistance is equal to rho times length by area. Here rho, which is the constant of proportion, is called specific resistance or resistivity. So, rewriting, we get R is equal to rho L by A, specific resistance or resistivity. Children, now let us see what is specific resistance. So, R is equal to rho L by A. Rearranging, we get rho is equal to R A by L, where R is the resistance of the wire, A is the area of cross section, L is the length of the wire. Children, consider a wire whose length is 1 meter and the area of cross section is 1 meter square. So, here is a conductor whose length is 1 meter, area of cross section is 1 meter square. Substituting the values, A is equal to 1 and L is equal to 1 in the formula, we get resistivity is equal to resistance of the wire. So, specific resistance is the resistance of that wire whose length is 1 meter and area of cross section is 1 meter square. So, the resistance of such a wire is called specific resistance. Specific resistance is constant for a material. Specific resistance for different materials are different, but resistance are constant for a particular wire. That means, if you have different wires made of same material, the resistances of those wires will be different, but all these wires which are different, if they are made of same material, the specific resistance for each and every wire will be same. So, specific resistance or resistivity of a material is defined as the resistance of a conductor of that material whose length is 1 meter and area of cross section 1 meter square. The SI unit is ohm meter. Children, here is the table which shows the specific resistances of various metals. Silver has the lowest specific resistance and then followed by copper, gold, aluminum, calcium and so on. You see that iron is somewhere below zinc and nickel, and graphite is the only material which will conduct electricity, which is a non-metal. And if we look at other substances like silicon, germanium, water, their resistivity is quite high when compared to the metals. Children, silver is the best conductor among all the naturally available metals and then followed by copper. Now, guess why we do not use silver wires when silver is the best conductor? Simple, silver is more costly, so we can compromise on that resistivity and hence we do not use silver wires. So, for better conductivity, we go for the next cheaper metal in the list, that is copper, and we use copper wires. Also, when we use wires at home, the length of wires is quite less and hence we go for copper wires. Suppose if you want wires over a long distance, for example, transmission lines which carry power from one power station to a city, or even at farmland, where there is a borewell at a particular place and then the transformer at another place. What happens is the length of the wire will be quite high. So, for more length we use less cheaper wire, that is aluminum. So, whenever the length is more, the amount of material required will be more and hence the cost will be more. So, to reduce the cost we go for aluminum wires. So, if you look at the table, silver is the best conductor, and wherever very high conductivity is required, only in those places silver is used, like mobile phones, specific electrodes in various devices, and whereas coming to copper, copper is used in wires for electrical wiring at homes and industries, and gold being very costly, we do not use it. Aluminum being the fourth best conductor, we use it only for long distance transmission of electrical power. Children, here you see there are some alloys which are alloys of various metals. They have quite high resistivity. So, wherever we require high resistivity, we use alloys of various materials. Children, let us do some numericals on the specific resistance and resistance. A wire has a resistance of 10 ohm, its length is 50 centimeters. It is cut into 4 equal parts. Find the resistance of each part. Resistance is directly proportional to length, and hence each part, which is 12.5 centimeters, will have resistance equal to 2.5 ohms. Children, now imagine if we have more than one device or more than one resistor, how do we connect them? So, if we have more than one devices, how do we connect them? We can either connect them in series or we can connect them in parallel. So, let us see what happens when they are connected in series or when they are connected in parallel. So, let us first study what happens when resistors are connected in series. So, here are 3 resistors R1, R2 and R3 which are connected in series. Here from the ends of R1 to end of R3, we see that the total voltage will be equal to the voltage across R1, voltage across R2 and voltage across R3. We can use the term voltage for potential difference. So, the potential difference across the combination is equal to the sum of potential differences across each resistor. So, let the resistance of the combination equal to Re. So, that is the effective resistance. Now, the potential difference across R1 is given by V1, potential difference across R2 is given by V2 and potential difference across R3 is given by V3. Applying Ohm's law, the current in each and every resistor will be same because all of them are connected in series. So, whatever current flows through R1 will flow through R2, also it will flow through R3, and then applying Ohm's law we get V1 is equal to I R1, V2 is equal to I R2, V3 is equal to I R3. Because the total potential difference will be equal to V1 plus V2 plus V3. So, we can write as V is equal to I R1 plus I R2 plus I R3 and V is equal to I R equivalent. So, substituting I R equivalent is equal to I R1 plus I R2 plus I R3. Current being same, we can write R equivalent is equal to R1 plus R2 plus R3. So, the resistance when connected in series, the resistance will be equal to sum of individual resistances. So, R equivalent is equal to sum of all the resistances which are connected in series. Children, so we can understand that if resistors are connected in series, the resistors of each and every resistance, that is the resistance of all the resistors is getting summed up. That means the resistance will be greater than the greatest resistance in the combination. So, the overall resistance will be greater than the greatest resistance in the combination. Let us study the parallel combination of resistors. Here are 3 resistors which are connected in parallel, and we can see that the current which enters the combination will get separated into 3, that is I1, I2 and I3. I1 passes through R1, I2 passes through R2, I3 passes through R3. Applying Ohm's law, we get I1 is equal to V by R1, I2 is equal to V by R2, I3 is equal to V by R3. Here the potential difference across each and every resistance is same. So, assuming that the resistance of the combination is Re, we can say V is equal to I Re or I is equal to V by Re. Substituting the values, we get V by Req is equal to V by R1 plus V by R2 plus V by R3. So, V being equal and common on both sides, we get 1 by Req is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So, in parallel combination, the overall resistance of the combination will be lesser than the smallest resistor in the combination. So, if resistors are connected in parallel, the overall resistance is going to decrease. That means the resistance will be lesser. So, wherever you want the resistance to be less, we can connect one more resistor in parallel. Children, let us do a numerical. 3 resistors 10 ohm, 20 ohm and 30 ohm are connected in series and parallel. Find the resistance in each circuit. So, the resultant resistance has to be found out. So, case 1, when the 3 resistors are connected in series, the resultant will be equal to R1 plus R2 plus R3. So, the resultant resistance is equal to 10 plus 20 plus 30, which is equal to 60 ohm. Now, when the resistors are connected in parallel, the equivalent resistance is given by 1 by R equal to 1 by R1 plus 1 by R2 plus 1 by R3. So, 1 by R is equal to 1 by 10 plus 1 by 20 plus 1 by 30, which is equal to 11 by 60. Taking the reciprocal, resistance is equal to 5.5 ohm. Children, let us solve another numerical. 3 resistors R1, 4 ohm and 8 ohm are connected in series in a circuit. If the resultant resistance in the circuit is 20 ohm, find the value of R1. So, resultant resistance in the series connection is given by R is equal to R1 plus R2 plus R3. So, substituting, we get 20 equal to R1 plus 4 plus 8. So, R1 is equal to 20 minus 12, which gives you 8 ohm. Another numerical, 2 resistors R1 and 12 ohm are connected in parallel in a circuit. If the resistance in the circuit is 3 ohm, find the value of R1. So, resultant resistance in parallel connection is given by 1 by R is equal to 1 by R1 plus 1 by R2. Substituting the values, 1 by 3 equal to 1 by R1 plus 1 by 12, and from this 1 by R1 is equal to 1 by 3 minus 1 by 12, which comes out to be 1 by 4. So, R1 will be equal to 4 ohm. Children, now let us revise. Electric current is defined as amount of electric charge passing through a cross section in 1 second. Electric current is equal to amount of charge flown in unit time. So, I is equal to Q by T. SI unit is ampere. Just like object rolls down when there is difference in height, electric charges move if there is potential difference, and battery maintains constant potential difference across the wire. Work done by the chemical force to move 1 coulomb charge from positive terminal to negative terminal in a battery is the potential difference across the terminals, that is called EMF, electromotive force. Ohm's law, The current in a conductor is directly proportional to the potential difference applied across the conductor at constant temperature. I is equal to V by R. Ohmic conductors are those which obey Ohm's law. Non-ohmic conductors are those which do not obey Ohm's law. Here the resistance is constant for the conductor at constant temperature. Ohm's law is valid only at constant temperature. Resistance of a conductor is the property by virtue of which the conductor opposes the flow of electric current through it. SI unit is ohm. The symbol of resistance is given in the figure. Resistor is that which offers resistance. If the resistance is very less, it is called a good conductor. If the resistance is more or very high, it is called a bad conductor or insulator. Factors affecting resistance. The resistance of a conductor depends on material length and area of cross section. Greater is the length, greater is the resistance. Lesser is the length, lesser is the resistance of a conductor. Greater is the area, lesser is the resistance, and lesser is the area of cross section, greater is the resistance. So, specific resistance or resistivity. So, the relation between resistance and rho is given by R is equal to rho L by A, where rho is the specific resistance or resistivity. Resistors, when they are connected in series, R equivalent is equal to R1 plus R2 plus R3. When resistors are connected in parallel, 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Children, with some more interesting topics, let us meet in another class. Till then, keep observing different things around you and try to predict what happens and how they happen, because physics is not only in books, it is around us. And we will meet in another lesson with much more interesting topics. Thank you.